Hello, this is my English speaking practice, and I'm talking about my tech study. And yesterday I've learned consistent hashing. Yeah, consistent hashing is a technique for distributing key across servers in a scalable way. It's widely used in distributed databases and key value stores. The idea is to avoid the inefficiency of the simple modular approach. With module, if you add or remove a server, almost all keys need to be reassigned, which is very costly. Consistent hashing solves this by organizing servers in a ring and assigning keys to the nearest server in the ring. This way, when servers are added or removed, only a small fraction of the keys need to be moved. That makes it very efficient for dynamic distributed system. And consistent hashing works by mapping both server nodes and keys onto a ring using hash functions. Each key is assigned to the first server in the clockwise direction. When a new node is added, it's placed on the ring, and only the keys that fall between the new node and the previous node are reassigned. This minimizes the amount of remapping, which is the main advantage over simple modular hashing. And today, with consistent hashing, I'd like to learn about the design of key value store. Key value store is one of the non-relational database. So as its name is, it uses the key and value, and yeah, so the consistent hashing works. Okay, I want to learn about how design the key value store. So I have to define the requirements, its requirements. Step 1, understand the problem and make it clear to make the requirements clear. Yeah, because there is trade-offs. So in this stream, I assume the following requirements. For example, the size of key value pair is small. It's about less than 10 kilobytes, and be able to store the big data, and high availability, high scalability, and auto scaling, and it can adjust the consistency and low latency. I will go with these requirements. How to do that? First, let's create a single server key value store. Hmm. 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 Okay, I will. Write it down. Single server key value store. It's simple. It's it's just it's just it just use the hash table for key value store, and hash table is loaded in memory, and it make it faster to access. But there is a limit of capacity, so it's impossible to store all of the data. So we have two way to optimize: data compression and to store the high frequency data on memory, and remaining to be stored in disk. Okay, so data compression and store high frequent on memory, and store lumens. Okay. But in order to have big data, it requires distributed key value stores. Distributed key value store is also called as distributed hash table, and it stores key value pair distributedly. So it's important to understand the CAP theorem. CAP stands for consistency and availability partition tolerance. Oh, let me distributed key value store is also called as a distributed hash table, and it stores a lot of key value pairs distributedly. And when designing the distributed systems, it's important to understand CAP theorem. CAP stands for consistency, availability, and partition tolerance. CAP theorem asserts that consistency, availability, and partition tolerance cannot be met at the same time. So let's define here about CAP. Consistency. All of the client can look up the same data, whichever any node the client connects. Availability. When a part of nodes is failing, the client that request for data can get a response. Partition tolerance. Partition means the connection between two nodes. Failed. And partition tolerance means even if there is a network partition, the system can continue to work. And in CAP theorem, the system can support two properties between them. So it means they cannot get a remaining property. Okay, so there are three types of key value systems. It supports C and P, consistency and partition tolerance. Second, A and P, availability and partition tolerance. And C and A, consistency and availability. Okay. A key-value store can also be implemented as a distributed hash table, which stores a large number of key-value pairs across multiple nodes. When designing such systems, it's important to understand the CAP theorem. CAP stands for consistency, availability, and partition tolerance. Consistency means all clients see the same data no matter which node they connect to. Availability means every request receives a response even if some nodes are down. Partition tolerance means the system can keep operating even if there are network partitions between nodes. According to the CAP theorem, a system can only fully satisfy two of these three properties at the same time. For example, some systems choose consistency and partition tolerance, others choose availability and partition tolerance, and some choose consistency availability depending on design goals. That makes sense. So my original version is like this. It seems to be trimmed a lot. But it's okay. And next. In ideal situation, there is never network partitions. So if the data is written to node 1, it automatically sync data to node 2 and node 3. It means consistency and availability, right? But for real, in real, We cannot avoid the network partitions in distributed systems. So when the network partition happens, we have to choose only one from consistency and or availability. Okay, so let's think the situation where the node 3 is down and node 3 is down, and so the node 3 cannot connect to node 1 and node 2. When the client writes the data, node 1 or node 2, the data cannot be sent to node 3. And likewise, when the data is written to node 3, the data cannot be synced to node 1 and node 2. It means node 1 and node 2 have all the data, right? So if you choose consistency and partition tolerance CP system, we call it CP system. Yeah, in order to avoid the inconsistency between servers, we should block the write operation to node 1 and node 2. It means you cannot use the system. For example, for bank system is required high consistency. So we should choose the CP system. Yeah, because it's very important to display the accurate balance to the client. So when the network partition happens in bank system, it is supposed to return errors. Return errors until we can achieve the consistency. On the other hand, when we choose the AP system, availability and net partition tolerance, the system might return all the data, but it can continue to accept read operations. And when write operation happens, node 1 and node 2 continue to accept write operations. And once network partition end and it is solved, it starts to sync data to node 3. So we can choose one of them. So it's important to consider use case and choose proper properties. Okay. Okay, so next topic. Next topic is system components. System components. Data sharding, data replication, consistency, solve inconsistency, solve. Recovery from failure. System composition. Write path. Read path. Data sharding. Data replication, consistency. Right path. Read path. Okay. If you run a large application, it's impossible to store all data in a server. A server. The most simple way is to split data into small partitions and to store them into multiple servers. However, there is two problems for data sharding. To distribute data equally for multiple servers. To minimize the data movement when node is added or removed. Yeah, so we can use the consistent hashing for these problems. It makes it possible to auto-scale and distribute data equally. In order to make the system high available and reliable, we need to replicate data asynchronously to some servers. For example, when we use the consistent hashing, we can use a ring structure. For example, we can choose the number 3, that is the number of servers used for data replication. So we can choose the first 3 nodes in clockwise direction. But when we use the virtual nodes, it can indicate the same node, same physical node. So in order to avoid this problem, we can use some logic to find the nodes. Additionally, the node in the same data center can be affected by the same failure, such as power down, network problems, or natural disaster. So for more reliability, we can choose the physical server, which is located in different data center. For consistency, this is a little bit complicated, so I will write it down. The data is replicated by multiple nodes. So it requires to synchronize the data between replicated datas. There is a concept we call quorum consensus, which assures consistency in both of read and write. So let's define the variable n. N is replicated data, number of replicated data. Okay. Number of and W is light quorum. Size W right quorum. When write operation succeeds, it needs to conform write operation from W size R of read quorum when read operation succeeds. It needs to wait for at least R of response. Replicated data. This means number of nodes. Okay, so for example, the number 3, there are 3 nodes, and there is a coordinator on the ring. So the coordinator requests write operation for each node. All right. Oh wait. How about W is 1. So the size is 1. It needs to confirm write operation 1 replicated data. So it means the write operation happens for each client. So when the n is 3, the write operation requests 3 times for each client, for each node. And when the w is 1, it needs to confirm write operation from 1 replicated data. So the coordinator requests 3 write operation, but it's okay to confirm the 1 write operation. Right. Okay. So the composition of WRN is a typical trade-off of latency and consistency. For example, the W or R is 1. It means the coordinator just wait for one response of them. So the operation is very quick. When the W or R are more than 1, the system can obtain the good consistency. But the coordinator should wait for multiple response, so the query is slow. When W plus R are more than N, Hmm. 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 Okay. Hmm. Okay. Okay. Let's talk about consistency model. Consistency model is what defines consistency of data, and there are a lot of consistency model. For example, strong consistency. It's mm, whenever you read, you can get latest written data. So the client never you never read the old data. Yeah, that is a strong consistency. And weak consistency, when you read later, you might read old data, and consistency final consistency, or I don't know the English translation. At the end. Sequential, eventual. There are three types of consistency. The strongest model guaranteeing that every observer sees the same data state immediately after write. Read returns the most up-to-date data from the latest write, regardless of where or when the request is made. essential for applications needing absolute data sovereignty, like banking systems, inventory management, or healthcare systems, can lead to higher latency and lower availability because operations might be delayed until data is visible across all replicas. Eventual consistency. A weaker model where data updates eventually propagate, and all replicas will coverage to the latest value if no further updates occur. That makes sense. Allows for temporary inconsistency between replicas, but assures eventual coverage. Convergence to a single value over time. Ideal for applications prioritizing high availability and performance, such as social networks, content delivery networks, and some e-commerce platforms. Users might see state data temporarily, which is accessible for many applications but not for critical financial operations. Weak consistency, the weakest guarantee, offering no strict rules known when or if replicas will reach a consistent state, permits significant divergence between replicas and allows for temporary inconsistencies used in systems where availability and performance are paramount. Temporary data divergence is accessible. Provides the highest availability but the least data integrity. That makes sense. For example, Dynamo, AWS DynamoDB, and Cassandra choose the eventual consistency model. Which is recommended to key value store. Okay. Okay, so it's time to review. Today what I've learned. I've learned about the design for key value stores. Before do that, it's important to understand the problem and its requirements. And for example, when I think about the key value store on a single server, it's simple. It just use the hash table for storing key value pairs on the memory, but there is a limitation. So it's impossible to store all the data in memory. As a way to optimize, we can compress the data and store high frequent data on memory and remaining data to be stored in disk. But it's not enough, so we use the distributed key value store. It's time to review what I've learned today. I've learned about the design of key value stores, and before designing it, we should understand the problem and make the requirements clear. Yeah. So first of all, I'd like to think about the key value store on a single server. It's simple because it just uses the hash table for storing key value pairs, and we can use it on memory. Yeah, because the memory access is very fast, but there is a limitation of capacity, so we cannot store all data on memory. So what we can do for that, we can compress the data and storing high frequent data on memory and remaining data to be stored on disk. Yeah, but for big data, we cannot handle it for single server, so we need distributed key value stores. And in order to design the distributed systems, we need to understand CAP theorems, which stands for consistency, availability, and partition tolerance. Yeah. Let's take a look at a definition of them. Consistency. All clients can read the data at the same time, no matter which node they connect to. Availability. Even if a some of data is down, the client who request for data can get a response. Partition tolerance. Partition means the network is disconnected between two nodes, and partition tolerance means system can keep working even if there is network partitions. And in CAP theorem, we can meet two properties, two of three properties, right? So it means we can not meet three properties at the same time. So there are three types of systems: CP system, AP system, and CA system. Yeah, that's a definition. Yeah. Okay. Why do you translate? Why do you translate? Let me see the translation. Store. CAP theorem. Okay, continue to next. Continue next. Hello.
Hey there.
I'm talking.
I'm here whenever.
I'm talking about the CAP theorem, or distributed key value store, and next topic is ideal situation. Ideally, there is no network partition. So if the node 1 is written the data written can be synchronized to node 2 and node 3 automatically, so we can achieve the consistency and availability at the same time. But for real, we cannot avoid the network partitions in distributed systems, so when the network partition happens, we have to choose one of consistency or availability. Does it make sense?
That makes perfect. I'm glad it does. Absolutely. Feel free to let me. Absolutely. great. Just let. I'm always here to help.
Okay. So the next topic is for the real distributed systems. So let's think about the situation where the node 3 is down. It means the node 3 cannot communicate with node 1 and node 2. So when the client writes data on node 1 or node 2, they cannot synchronize the data to node 3. And also, if the node 3 is written data and it have not synchronized data to node 1 or node 2, it means node 1 and node 2 have old data. Okay, so if you choose the CP system, so you choose the consistency rather than availability. The systems to avoid the inconsistency, it have to block all of write operations to node 1 and node 2. Okay.
Absolutely.
Yeah, it means the users cannot use the systems. For example, banking system or critical financial systems. Yeah, choose the CP system.
Exactly. The example you mentioned.
Okay. On the other hand, you can choose the availability rather than consistency. So the system might return old data, but the system continue to accept the read operations. So node 1 and node 2 also can accept the write operation, and once the network partition is solved, the data synchronize will start. Okay.
Absolutely.
Yeah, okay. Okay, so the next topic is system components in distributed systems, and today I've learned about data sharding and data replication and consistency models. For data sharding, it needs to split the data into small partitions, and that corresponds to the multiple servers. Yeah, but there is two problems in the data sharding process. The first one is the difficult to distribute data equally onto or multiple servers, right? And the other one is to minimize the data migration when the node is added or removed. Okay.
Exactly. That's a key.
I see. So I enable the mic, so the mic take a sound from the display, so it's like a loop, so the ChatGPT cannot respond to me correctly. That's my bad. Okay, today I've learned a lot, so it's time to finish. Thank you for watching. See you tomorrow.